the potential energy is zero essentially, but it's been changed into kinetic energy. So you can go back and forth between potential energy and kinetic energy. You can turn your potential energy into kinetic, so you gain kinetic and you lose potential is the thought there. And that's very common, not just kids. All sorts of substances can change the amount of potential energy that they have. If a substance goes through some sort of change where it gains potential energy, we call that reaction a spontaneous reaction, or an exergonic reaction, or sometimes a downhill reaction. There's a diagram using water as an example. If you allow water to flow over the dam, the water is losing its potential energy, essentially changing it in for kinetic energy. But since the water has lost potential energy, you say that it is a spontaneous reaction, a downhill reaction. Now, let's see. Here we go. Oh yeah. So as the substance, like the water behind the dam, is losing potential energy, the energy is being released in the reaction, and we can tap into that lost energy, the energy that the water is losing, to be an energy source. And using the dam as an example, as the water flows down the dam and loses potential energy, we capture some of that and change it into electricity. I think this is some sort of electrical generating plant right here, and that powers our light bulbs and elevators and things like that. So any spontaneous exergonic downhill reaction can potentially be an energy source. Now, if we look at the flip side of that, or the opposite case, if we have some water that at a low elevation and we want to raise it up to a higher level, that would be a gain of potential energy for the water. And we call any reaction like that a non-spontaneous or endergonic or uphill reaction, any change in the substance where there's an increase in the amount of potential energy. And we know from common experience that water doesn't flow uphill. So no substance is going to want to undergo a non-spontaneous reaction where it gains potential energy on its own. Just in our universe, that type of reaction just doesn't happen. Now, if you really are dead set on getting that water uphill, you can do it, but you have to pump it uphill. You have to get some sort of electric or powered pump of some sort to force it to go to gain potential energy. And so you can do it, but you have to supply it with energy. And so the way I think of these is, though, if the substance is losing potential energy, you can get energy out of it, but if the substance is gaining potential energy, you have to put energy into it to make it occur. Now, getting back to that hydroelectric dam for a second. Let's see. Here we go. If I were to go over to the elevator at the end of the hallway, a lot of people don't know it, but we do have an elevator in this building. If I were to go over to the elevator at the end of the hallway and jump inside of it and go up to the second floor, is that a spontaneous or non-spontaneous reaction for me? Non-spontaneous, because I'm gaining potential energy. Good. But we know that that's not going to happen. That elevator's not going to go anywhere. It's not going to do a non-spontaneous reaction unless I supply it with energy, which in this case is electrical energy. But we get energy from spontaneous reactions. So what I'm saying is, somewhere, I don't know exactly where, probably in the Sierra Nevada foothills, there's some sort of substance like water that's losing energy, losing potential energy, and we convert that into electrical energy and send it to Hartnell so that I can undergo this non-spontaneous reaction where I gain potential energy. And so that sort of arrangement has a name. It's called a coupled reaction. That just means where a spontaneous process, like the water going downhill somewhere in the Sierra Nevadas, I guess, is acting as the energy source to provide energy to make a non-spontaneous reaction go. Well, now that I think about it, maybe we get our energy from over at Moss Landing. They do have an electrical power plant there, but you see the point I'm making, that somewhere there must be a spontaneous reaction occurring to provide energy for our elevator to make it go. And that's a coupled reaction where one drives the other like that. Okay, now, cells, in a way, are like us living in our society. We want energy available to us so we can do the things that we want to do. Cells need energy to stay alive, to carry out all those metabolic reactions that they need. And so cells are very interested in having potential energy stored up somewhere inside themselves so that they can have all the energy that they need. Just like you like a gas tank full of gasoline in your car, so you'll know you can drive wherever it is that you want to drive to. Now, how exactly do cells store up their potential energy? Well, cells do not have gasoline tanks, exactly, and cells don't have little water reservoirs inside themselves or little hydroelectric dynamos and things like that. But nevertheless, they do have ways of storing up potential energy for themselves. And here the two major ways are: cells can store up potential energy by having something called a concentration gradient across their membranes, and they can also store up potential energy in terms of something called chemical potential energy, which you can think of as high calorie, high energy molecules. And let's do this one first, about the concentration gradients across membranes. If you imagine getting a glass of water and putting a drop of ink into it, the ink molecules are the solute molecules because they're molecules dissolved in a liquid. And when you first put that drop of ink inside there, all those solute molecules are going to be clustered together right there, whereas you're going to have very little, if any, ink molecules further out right there. Well, that initial arrangement of all the ink molecules clustered together next to the areas where there are no ink molecules has a name. It's called a concentration gradient. Anytime there are adjacent areas or neighboring areas with very different concentrations of a solute, that is a concentration gradient. And so you would just say that they're at a high concentration here and the solutes are at a low concentration there, and that's a gradient from high to low. Now, if we just let that drop of ink in the water sit there for a few minutes, you know what's going to happen. It's going to spread out a little further, and then a little further still. That process of the solutes spreading themselves out, or as some people say, moving down their concentration gradients, going from high concentration to low concentration, that spreading out has a name. It's called diffusion. And this is the official way that diffusion is defined, but don't let all the verbiage fool you. It's just a fancy way of saying solute spreading out. It's defined as the spontaneous movement of a solute from an area of high concentration to an area of low concentration. And let me click backwards here for a second. There we go. And you know, it sort of makes sense that here the solutes are at a high concentration, here they're at a low concentration. So as they spread out, they are moving from the high concentration area to the surrounding low concentration area. So it is diffusion. And a key word to notice here in the definition of diffusion is that it is a spontaneous process. And remember, that term has special meaning to us. It means that the molecules are losing potential energy. When they were all clustered together at a high concentration, that equals high potential energy, and the more they spread themselves out to lower concentrations, that equals lower potential energy. Like that, there's the potential energy diagram. And this is another thing we're going to be talking about quite a bit in this lecture is how diffusion equals a loss of potential energy for the solutes. And so whenever we say high concentration, maybe in your mind think high elevation, and wherever we think of lower concentration, think lower elevation. And if you can make that link between concentration and elevation in your mind, a lot of this will make more sense, because you'll say, okay, a diffusion is going to be a loss in potential energy, just like water going from high elevation to low elevation is a loss in potential energy. Now, all solutes want to diffuse. It's not something magical about red ink molecules, sodium ions, glucose molecules dissolved in water, potassium, you name it. Any sort of substance, any sort of solute molecule will always want to diffuse outward. It's just a natural process. Now, cells are able to store up energy by concentration gradient. Since a concentration gradient with where all the solutes are at a high concentration is stored up energy like water behind a dam, that's essentially what cells do. The dam is a membrane, a phospholipid bilayer. And remember that since the membrane, especially the interior portion right here, is extremely hydrophobic, solutes don't want to cross it, because most solutes are very hydrophilic. Just because the liquids outside and inside the cell are mostly water, and so by virtue of that, the solutes that you find there tend to be hydrophilic. So the membranes of the cell play the role of the dam, and the solute molecules play the role of the water. Now here I'm going to be using hydrogen ions as the solute molecule, because oftentimes these are the solutes that cells use to create concentration gradients out of for the purposes of storing energy. But I want to make a point here that it doesn't necessarily have to be hydrogen ions. If the cell had a huge concentration gradient of glucose molecules on one side and very few glucose molecules on the other, that would still be like a bunch of water stored behind a dam, and so that would be stored up energy, or sodium ions, or